Hi everyone, this is Kiyun from the University of Edinburgh, and thanks for your interest in our work. Today we're going to talk about improving efficient 2D backbone-based action recognition models. We're trying to solve a problem of action recognition, and in this task, the input data is a video, and given that video, we need to classify actions that are present. Let me introduce the standard pipelines of this task. This is an example of a 2D action model called TSN. First, we need to sample n image frames from the video, and each of the frame is represented with R, G, and B channels. Each image frame is fed into the 2D CNN model, and each of the 2D CNN model will produce per frame predictions. Finally, the video prediction would be the average of all the frame predictions. By the way, the backbone model has shared parameters, so we don't need to have any different copies of this 2D CNN backbone, which is why it's so efficient. On the other hand, there is a 3D or transformer model, and they utilize all frame spatial temporal features in one model. For example, the 3D CNN will perform 3D space and time convolutions. The model would then produce the predictions in the end. These types of models are typically much more expensive than 2D CNN models. Let's take a look at the performance versus inference time figure. The x-axis of the figure is the inference time in log scale. The y-axis is the performance of the model in accuracy. The line here you see are all 2D CNN based models, and they perform blazingly fast while having a competitive performance as well. On the other hand, the other models can take hundreds of times more time to train and test. Our goal is to improve these efficient 2D CNN models by this much. Let me start introducing our methods. In this example, we have an 8-frame model that takes 8 images as an input. We first need to sample 8 frames from the video. The baseline RGB representation of the 8 image frames looks something like this. In our time color reordering method, we reordered the frames and the color channels to look something like this. Notice that each frame in this representation contains 3 time frames of information. As an exception, the last 2 representations have duplicates of the last frame because we didn't have access to the future frames. To fix the duplication issue and generate more consistent representation for all frames, we also propose a variation of TC reordering called TC plus 2. Here we sample 10 RGB frames, and notice that we are sampling 2 more frames than before. We form 8 frame TC plus 2 reordered images, and this video representation has each image with 3 frame information consistently. The next method is inspired by the fact that humans don't have issues recognizing action in grayscale videos, as you can see in these videos. Can you tell what they're doing even though you don't have color information? Is color really necessary in action recognition? By foregoing the ability to reason about color, we can instead sample more frames. Here we sample 9 RGB frames, and first we converted them into grayscale. We can stack the 3 consecutive frames to form one grayscale stacked frame. We call this grayscale short-term stacking, or GrayST. This is an example of 3-frame GrayST, and if you have a model that takes 8-frame input, you need to sample 24 frames. This is an example video from something dataset labeled as pushing something from left to right. This is a time color reordered video representation. Imagine you were a 2D model that can only see 1 frame at a time. Is it easier for you to tell which direction the object moves in the TC reordered representation? This is a GrayST representation, and it has more fine information than TC reordering because we sampled more frames. It has been known that many action datasets have object and scene bias, which means that even if we hide the actors or actresses from the videos, we can still tell the action by the background or the object in the video. This can give extra advantages on 2D model performances, which is misleading. Since we wanted to prove that our methods capture more temporal information, we chose to evaluate on more temporal, challenging datasets. The first dataset is called something something. You can see that the labels focus more on the action than the object and the scene. Another dataset is called Cater. This is challenging because it involves multiple objects and their actions, plus temporal ordering of every pair of actions in the video. The K2 dataset comes with static and camera motion version. We mainly focus on these 4 2D networks. TSN is the one I showed you earlier, where it just averages the prediction of 8 different image classification results. TRN has a relational reasoning at the end of the model. The TSM shares CNN feature information throughout the frame in the backbone. Lastly, MVFnet adds channel-wise convolution, for example, height and width convolution, height and time convolution, and width and time convolution, instead of treating height, width, time 3D convolution like 3D models would do. This is an experiment results on the something something dataset. The x-axis is the model we use, and the y-axis is the accuracy difference compared to using RGB sampling. So by using our sampling method TC, TC plus 2, or GrayST, we can improve up to 20% of accuracy using the TSM model. However, the more temporal reasoning the model already has, the improvement is not as significant, although we still see consistent improvement overall. Here's a result on something something version 2, and the trend is very similar. It has a bigger improvement on the more naive model, but once it has more temporal reasoning already, the improvement becomes not as significant, but we still see consistent improvement overall. The result on the K2 dataset tells us the same thing. With TSN, we see up to 24% of improvement, and the improvement becomes less significant when it comes to TSM or MVFnet. However, we still see consistent improvement overall. Lastly, there's K2 camera motion dataset that involves heavy camera motion throughout the video. Here we see some of RTC methods fail on some models. However, we observe that the GrayST sampling improves consistently on all models. The decrease in performance is up to 2% and is not as significant as the advantages we saw. In summary, we improve performance of efficient 2D action models while incurring no additional computational cost, not modifying the underlying model, so the methods are compatible to most existing architectures. We also show extensive experiment results on several models and datasets to prove the efficiency of our methods. Thank you so much for watching the video and having interest in our work. Please check out our paper for more results on more datasets. The GitHub page includes the link to the paper as well. Thank you.